Hey guys, it's Mrs. Suderman. I hope you are having a good Friday afternoon, evening, or weekend. Real quickly, we're going to learn about Cramer's Rule. To find out more information, check out Chapter 4, Section 4 of your textbook. You can use the determinant of a matrix to help you solve a system of equations. For two equations with two variables written in ax plus by equals c form or standard form, you can construct a matrix of the coefficients of the variables. So for this system, a1x plus b1y equals c1 and a2x plus b2y equals c2, the coefficient matrix, the first column will be made up the coefficients for the x values, and the second column the coefficients for the y values. The coefficient matrix for a system of linear equations in standard form is the matrix formed by the coefficients for the variables in the equations, like we just saw. So the determinant of the coefficient matrix is, it looks the same except now because we're looking for the determinant, it's the straight vertical line brackets. So here's Cramer's rule, which will allow us to solve for x and y given a system of two linear equations. So you'll see that x equals, and they have something similar to the coefficient matrix in the numerator, but instead of the x values being in the first column, the coefficients for the x values in the first column, because we're solving for x, that column has been replaced with the constants, c1 and c2. And then the determinant of that is divided by the determinant of the original matrix. And when we're solving for y, again on top we have something very similar to the coefficient matrix, but the coefficients for the y values, b1 and b2, have now been replaced by c1 and c2, the constant terms, because we're solving for y. Then you would take the determinant of that and divide it by the determinant of the original matrix. You can use Cramer's rule to tell whether the system represented by the matrix has one, none, or infinitely many solutions. So if the determinant is equal to 0, the system is consistent and has one unique solution. If it equals 0, we have one of two options. If the numerator of the determinant is 0, like before where we've made some adjustments to the coefficient matrix before dividing to solve for x or y. If one of the numerators is equal to 0, it has infinitely many solutions, and if neither is equal to 0, it's inconsistent and has no solution. So if that's a little confusing, just hang on, we're going to work a couple of examples. Okay, so let's look at this example. We're going to use Cramer's rule to solve each of the following system of equations. So now we have 2x plus y equals 10 and 3x minus 2y equals 8. Always check first to see if the system is in standard form, ax plus by equals c. Here it already is, so we're good to go. So step 1 is to find D, the determinant of the coefficient matrix. Well, the coefficient matrix will be 2 and 3, because those are the values in front of the coefficients in front of the x's, and then 1 and -2, which are the coefficients in front of the y values. So there's the coefficient matrix. We need to find the determinant of this. So that will be D equals the determinant of 2, 3, 1, -2. So the determinant, we take the first diagonal, multiply those together, then we'll subtract the product of the other diagonal. So here we get -4 minus 3, and that equals -7. -7 is not equal to 0, it's non-zero, therefore the system is consistent, and there will be exactly one solution. So here's step 2. Solve for each variable by replacing the coefficients of that variable with the constants as shown below. So here are the little formulas that we got from that Cramer's rule table just a minute ago. And this is what we're going to do to solve for x. In place of the x coefficients, we've replaced those with the constants. And then the y coefficients stay the same, and then we'll divide it by the original determinant. So the constant terms are 10 and 8, and then the y coefficients were 1 and -2. Then we're going to end up dividing that by the determinant of the original coefficient matrix, and that was -7. So on top, the determinant of this will have -20 minus 8. Well, that's -28 over -7, and that equals 4. Okay, that one's not equal to 0, so let's check the other one and see if that one is equal to 0 or if we get a solution. So here, because we're solving for y, we'll leave the x coefficients the same, which were 2 and 3. And the y coefficients, we took those out and replaced them with the constants because that's what we're solving for. So here, the 10 and the 8 will be in the second column. And the determinant of the coefficient matrix was -7. So now we need to take the determinant of our numerator. So 2 times 8 minus 3 times 10. So we'll get -14 over -7. That gives us a value of 2. So therefore, the solution for this system is the point, or the ordered pair, for 2. Let's look at another example. So again, let's use Cramer's rule to solve the system of equations. First step, always make sure that it is in standard form. Here, these are not in standard form, so we need to do some adjustments on them. So we're going to move over that 2y, move back the 5, and so on. So now our system in standard form is going to be 3x minus 2y equals -5, and then 9x minus 6y equals -15. Now that our equations are in standard form, we can proceed by finding the determinant of the coefficient matrix. So here are the equations in standard form again. So it's easy. The determinant of the coefficient matrix, our coefficient matrix is 3, 9, -2, and -6. So we multiply the first diagonal, subtract the product of the second diagonal. So we get -18 minus -18, or plus a +18, and that equals 0. So because the determinant equals 0, if you look down, it's already told you that there, the system is either inconsistent or dependent. So it either has no solutions or infinitely many. So to determine which one, we're going to check the numerators for x and y to see if either is equal to 0. So the constant terms, because we're solving for x, will take the place of the x coefficients in our coefficient matrix. So we'll have -5 and -15. And then we'll leave the y coefficients the same, so we'll have -2 and -6. We'll divide that by, well, okay, so we're not really dividing, right? Because if we divide by 0, that's undefined. So let's leave that off. Just find the determinant of this matrix, and that equals 0. We could stop there because the rule is that as long as at least one numerator is equal to 0, then the system is dependent and has infinitely many solutions. But just for the purposes of this example, let's check the other one as well. So here the numerator will be 3 and 9. Those are the x coefficients. And then the y coefficients have been replaced with the constants, which are -5 and -15. That equals 0 as well when we take that determinant. So as it turns out, both of these were equal to 0. We only needed one. But since at least one of these has a determinant of 0 for this numerator, the system is dependent, and it has infinitely many solutions. So now that you've seen a couple of examples, here's one for you to do. Use Cramer's rule to solve 4x plus 3y equals 30 and 5x minus 6y equals 31. Be sure to show all of your work for this example in your notes, and I will see you on Monday. Have a good weekend. Bye.